2.8 trillion parameters, 1 million token context window, native vision, open weights, and it still beats every open source model in the world, sitting just behind Claude Fable 5 and GPT 5.6 Soul on almost every benchmark. This is Kimi K3, released by Moonshot AI this year. Hello everyone, welcome back to the channel. Today we will code every novel architectural idea in it from scratch in PyTorch. And here is a slight change in our pedagogy. Initially in our from scratch playlist, we used to first discuss the intellectual idea, then code immediately after. But in this video, we will first understand the complete architecture of Kimi K3, then we will return back and code it line by line. So let's get started. Before we dive into each component in isolation, let's use the sketchpad in the way it's meant to be used. So on your left, you can see the full stack top to bottom in like output, then one macro block, then three macro block, then embedding at the bottom. Let's hover on each one of them and understand what it is. So starting at the bottom, there are like 4 tokens go in the cat, sat, on and on, these 4 words, and each one is just an ID until it hits the embedding lookup table. That is 160,000 vocabulary entries by 7168 dimensions. Think of this as looking up a word in multi-dimensional dictionary, where each word gets 7168 number, like coordinate map, and one lookup and each token become a single d-dimensional vector. The vector is what block 1 actually sees. Nothing fancier than a lookup, like table lookup, happens here. All the interesting work is still ahead of it. Now if we go on to the second block, that is the 3 times the block of KDA plus table latent MOE. We will understand these in coming slides. Moving up, this blocks repeat 3 times. This is where most of the sequence length work happens. Watch the token flow from left to right through the arrow chain in KDA's recurrent state. Order of 1 memory, no growing cache, no matter how long the sequence gets. Underneath, stable latent MOE lights up. Out of 896 experts, only 16 fire per token. Here miniaturized to a 5 expert demo with 2 lit. And notice the orange arrow feeding in from below. That's the attention residual pulling in a signal from earlier blocks, not just the immediately previous layers. Now moving on to the block above, 1 layer up, and only once per macro block we hit gated MLA. This is the opposite trade-off from KDA instead of compressed recurrent state. It's full global attention. The heat map you see is a causal attention matrix, every token attending to every earlier token. No shortcuts whatsoever. Then a gate multiplies the result, same full rank gating pattern KDA uses. And finally the output one, at the very top, the LM head, it's just a softmax over the full 160,000 token vocabulary. But visualized as a bar chart, it makes the point clearer. Given the sentence the cat sat on, the highest bar is predicted as the next token as the word mat. That's the whole stack embedded once. Repeat the KDA plus MOE block 3 times, run 1 gated MLA plus MOE pass, and stack the whole unit 93 layers deep, 69 KDA layers and 24 MLA layers in total before reading off the output. Now let's zoom in into each piece and understand why it's built in this way, starting with KDA. But before that, we will also discuss the roadmap or the blocks in the category in which each component falls for this architecture. So let's move on to that. Okay, so if you see here, the Kimi K3 paper introduces 11 novel contributions, and this sketchpad groups them the way I think about them, like along the same three dimension I'm about to introduce. So group A is context and memory, and it has KDA recurrence, gated MLA, and a KDA context parallel component. We will understand these, don't worry about that. Group B is attention and signal flow. It will be full attention residual and block attention residual. And group C is like expert and training, stable LatentMoE, SiTU-GLU, Quantile Balancing, MXFP4 experts, per head Muon, and multi-teacher OPD. Today we are implementing the core architectural ones, the ones marked with check mark here, and the one that define how Kimi K3 processes information. The lightning bolt item need a distributed infrastructure beyond a single GPU, and the clipboard item you can see here is a post-training stage that needs a fully trained model first. By the end of this video, you will have implemented a working miniature Kimi K3 in PyTorch with all 7 architectural innovation from scratch. So let's start from the first topic, that is KDA recurrence. So let's first understand the first component, that is KDA or Kimi delta attention. KDA is the most important and most novel component in Kimi K3. It handles the sequence dimensions, like how information flows across 1 million tokens. If I reload it or like this slide, you can watch this canvas, like as it builds, it runs through 4 phases automatically. First, the recurrent state chain appears, then the per channel decay bars, and then the update equation, and then the read equation happens. Let's go through what each one means. The core problem KDA is solving is like in standard attention, the standard self attention is of order of n square in sequence length. So for 1 million tokens, that's 10 to the power 12 operations per layer, completely infeasible. So in simple terms, like consider standard self-attention is like being in a room with 1 million people, where every time someone speaks, every single person has to reread notes on what every other person said before them. By token, like 1 million, your notebook is a million page thick. So the KDA solution is, instead of keeping every page, you carry a single whiteboard of fixed size, let's say S of t. As each token speaks, or like each person speaks, you take an eraser, wipe off conflicting old information with the new takeaway, and pass the same whiteboard to the next token. Your notebook never grows. That's order of 1 memory, better than order of n square, much better than order of n square. So look at the recurrence rule on the screen. Like S of t is like 1 minus beta t dot of k of t and k of t transpose, and the diagonal alpha of t dot product of S of t minus 1 plus beta t dot kt and vt transpose. And the O of t will be S of t dot product with Q of t. That is the query. So let me unpack this because it maps directly to our whiteboard operation. The diag of alpha t dot S t minus 1, this is the fading board. The alpha t vector is a channel wise decay vector. Look at the bar chart phase on screen. Each bar represents a different channel. Like fast decay channel fades quickly, short-term memory, while slow decay channels stay visible for thousands of tokens. That is the long-term memory. The second formula is like that, this I minus beta t dot kt and kt transpose. That is the eraser part. This is the delta rule. Before writing new information, if the new key KT covers a topic already on the whiteboard, it actively erases the old representation in that specific direction. This prevents contradictory information from piling up. And the third one is plus beta t dot kt and vt transpose. This is the marker, the write operation basically. We write the new key value pair onto the freshly prepped whiteboard scaled by the beta t. And O of t, that is the output or the reading part. The query qt inspects the current state of the whiteboard to read out the answer. The lower bound decay fix is like in previous linear attention models like Kimi linear, the log decay g was unbounded, minus infinity to 0. Like unbounded decay is like using ink that fades to complete invisibility, or when calculated backwards on a computer becomes infinitely bright. Mathematically, multiplying number near 0 over a million token sequence causes floating point number in like B float 16 to crash into 0 or explode into not a number infinity. So Kimi K3 fixes this with the scaled sigmoid. It has g equals to gmin dot sigmoid of exponential of a dot z. And this belongs to gmin comma 0, where gmin is equals to minus 5. So by bounding log decay below by minus 5, retention never drops below e to the power minus 5. That is roughly around 0.0067. It keeps the number strictly inside B float 16's safe zone. This allows GPU tensor cores to process chunks of token into dense matrix operations without crashing or requiring slow custom workarounds. The stat cards at the bottom summarizes it like 0 of 1 memory decay, 0 of 1 memory required, decay range is 0.0067, 1 and 69 of 93 layers in K3 are KDA. So next we move on to a gated MLA, that is global attention without positional encoding. And you will also see as I move to next slide, the diagram also highlights where in that architecture that particular component sits. So if you see, if I move from the KDA slide, the KDA was highlighted here. Now it is on the gated MLA. So this was just a small specification so that you can follow. So right, okay. After 3 KDA layers like comes on the gated MLA layer. MLA stands for multi-headed latent attention. Originally from DeepSeek V2, Kimi K3 uses it as the global attention component. So let's step through each stage shows. Stage 1 is 8 tokens sit at full hidden width like D equals to 7168. Stage 2, watch them compress down into narrower latent like bottleneck, which is just a quarter of the model width. Stage 3 is the latent decompress back out in the K and V. And stage 4 is the casual attention heat map fills in, like every token attending to every earlier token. The analogy can be like, imagine a busy airport luggage system. Standard attention sends full-sized shipping container, let's say D equals to 7168, to every gate KV cache, causing massive traffic jams. MLA acts like vacuum compression bags. It squishes every token's key and value information down to tiny pouches, of like the cache size of KV cache size of 1792 to store in the memory. Only right when the attention calculation happens does it unzipper the bag back to full size. So notice something missing in MLA. There is no positional embedding, and you may ask why. So think of KDA and MLA as a timestamped ledger versus an index search. KDA handles time because its recent whiteboard naturally processes sequence order step by step. Token 200 inherently knows it came after token 100 because of the state decay chain. Because KDA already bakes time directly into the signals passing up through the network, MLA doesn't need to wear a watch or the positional encoding. Like it can focus 100% on pure content search, matching queries to keys anywhere in the document regardless of the distance. And because there is no positional embedding, like base frequency in MLA, you don't have to retune positional math when extending context to 1 million tokens. So next we move on to the attention residual part of this architecture. This is one of the most elegant ideas in the paper. Like let's understand the problem it solves first, then we will understand how it's solving. Consider the analogy or the game, like the game of telephone. In a standard transformer, layer 1 passes its output to layer 2 to layer 3, and so on and so forth, up to layer 90. This is like playing a 90% game of telephone. By the time the message reaches person 90, the original word from the person 1 are muffled and distorted under 89 layers of noise. Standard residual connection try to fix this by adding input together, but after 90 additions, early signals are still buried. So attention residual solves this like depth bottleneck by like instead of passing a whispered note down a line of 90 people, attention residual gives layer 90 a mixing console and with 89 direct microphones plugged directly into each previous layers. Layer 90 can turn up the value of layer 90 can turn up the volume slider and on layer 1 signal directly. Like no need to pass it on from one person to another person and to another person, or one layer to another layer or another layer. As you can see in the diagram as well, that it's connected like to all the 90 layers or at a single time. So look at the bright connection lines on the screen. Layer L has learned pseudo query, that is WL. It runs softmax over all previous layers output, and this is the like full attention residual. And the block attention residual is like keeping all 93 output in GPU memory to full attention. For full attention rest is like expensive. It has the order of L square memory. So like notice how the diagram simplifies from 12 individual layer connection down to just 4 blocks summary connections. So Kimi K3 groups it like 93 layers into 8 macro blocks. Each block sums its internal layer output into a single block summary. Then layer L only attends over the 8 block summaries. So like if I give you a simple analogy, instead of plugging 90 individuals microphone into your mixing console, you route 12 people per table in 8 groups, group submixers, and adjust 8 master slider on your board. So memory drop from like order of L dot D down to order of N dot D with zero loss in single clarity. So this helps as it reduces the memory, and we are not even dropping the quality here. So next we move on to the stable latent MOE. Basically, the feed-forward network in each layer is replaced by a stable latent MOE. Let's look at how it scales the width. In standard mixture of expert, you have a room of full expert specialist or experts. A router evaluates incoming token vector and send them to the best specialist. Kimi K3 has 896 routed experts, and for every token 16 active experts are chosen. So consider like sending a full sized 7168 dimensional token to 6 different expert is like mailing 16 copies of a full encyclopedia set across a network every single layer. It creates massive inter GPU traffic bottleneck. So latent MOE solves this by splitting width into two distinct tiers visible as two rows on a screen. So the first one is the shared expert, the green row. It has the full width of D equals to 7168. They are always active for every token to process core baseline knowledge. The second is the routed expert or the blue row, these ones. Compressed, these are the compressed latent width with L equals to 3584. Instead of mailing full encyclopedia to experts, latent MOE compresses the token down to a pocket summary. That is L equals to 3584, and routes that lightweight summary to 16 experts and gets their specialized work back and then expand it back out. So this cuts the cross GPU network routing bandwidth in half, and hence it helps in scaling the width dimension. So now let's consider the SiTU-GLU bounded activation stability. Consider this: when you stack hundreds of matrix multiplication in across 896 experts, deep network face a catastrophic risk of activation explosion. Look at the dashed gray line on the screen. The standard SiTU-GLU, sorry if I'm mispronouncing the word, activation are like SiTU-GLU activation are unbounded. As input number grows, the output curves rockets off towards infinity. In 16-bit or 8-bit precision, it hits maximum value limit instantly, causing numeric overflows like NANs or infinity. The analogy can be like SiTU-GLU is like an accelerator pedal with no floorboard stop. If you press down hard, the engine revs until it literally explodes. And the SiTU-GLU installs a soft physical speed governor or a soft cap on the pedal. So look at the solid pink curve flat line that flattens out against the dashed bounds. The beta dot tan h the beta dot tan h of x divided by beta terms acts as our soft governor here. Near zero, it behaves with the exact same expressive smoothness as a SiTU-GLU. But if the input grows, it cleanly levels out at a max ceiling off. So no matter how extreme the input, activation value never exceeds 100. Overflow are mathematically impossible for this example. Next, let's move on to the quantile balancing, that is expert loading balancing at scale. With the 896 experts, you run into a huge problem, that is the load imbalance. So consider, like, imagine a hospital with 896 special doctors. If all patients flock to the same 16 famous doctors, those 16 get crushed with work, while the other 880 or so doctors sit idle getting paid for doing nothing. Standard auxiliary losses try to nudge router scores, but they degrade model performance and adapt too slowly. Kimi K3 uses quantile balancing, or QB for short, to achieve perfect load balancing in a single forward pass without corrupting the gradient. So look at the panel on screen. Panel A, that is the unbalancing dispatch. Expert 1 is overloaded with 4 tokens, while expert 4 gets 0. And panel sorry, C has the quantile balance dispatch. Every expert gets equal or evenly distributed tokens, 2 tokens each in this case. So like QB acts like a automated host at a busy restaurant. Instead of adjusting food recipe like gradients in terms of LLM, to get people to pick empty tables, the host simply calculates the exact weighting line of scores, that is the quantile, for each table based on current queue, and adds a temporary door bias, that is B of J in this formula. So every room fills at the same exact target rate. By using a fast histogram binning method to compute this cutoff across GPU clusters, Kimi K3 balances routing load instantaneously across all 896 experts. Okay, now next let's discuss the per head muon, the optimizer part of this architecture, or Kimi K3 architecture. To train this monster, Kimi K3 uses a novel optimizer variant, that is this per head muon. So standard muon applies Newton Schul's iteration to orthogonalize gradient weights update, ensuring updates preserve matrix structure without exploding or shrinking weights. So look at the two side by side boxes on the screen. Left box, standard muon, takes entire D cross D gradient matrix and orthogonalize it as one massive block. The right box is per head muon, slices the matrix into head size stripes and orthogonalize each head independently. The one analogy can be like, imagine a classroom where 16 students, in this case heads, take a group test, and standard muon assigns one overall group grade adjustment based on the class average. If student 1 shouted loudest, their work dominates the grade, while quiet student 16 gets ignored. So this was a general analogy, whereas the per head muon gives every individual head their own private tutor. Each head's gradient update is normalized independently based on its own scale. So quiet heads learn at the same pace as the loud heads. The equation card at the bottom shows the Newton-Schulz polynomial iteration applied per slice head. Now, since we have the full picture, like every component visualized, every dimension scaled, and every mechanism grounded with intuitive analogy, so let's jump on into our VS Code and code Kimi K3 from scratch in PyTorch. So let's move on to our editor. Okay, so now we are in our Python file in our VS Code editor. So let's start by importing the required libraries, that is import torch torch.nn as nn, import import torch dot nn dot functional as f and import math and from typing we will import optional tuple and list. From data classes we import data class and we will set the manual seed to 42. Okay, so this is the import statements or the libraries or modules we need. Next, let's configure the model configuration. Write the model configuration. So this will have class as Kimi. Let's name it Kimi K3 config, and this will have a decorator data class. Then inside this we will assign d model as int and 512 dimension, number of layer, d model is dimension of model, number of layer int equals to 16, number of heads will be 8, this will be also int and equals to 8, and then we have dimension of each head again int, and this will be 64. So this dimension of head is basically dimension of model divided by number of heads, and number of layers is equals to 16 because it has 12 KDA layers plus 4 MLA layer. So the ratio is 3:1 to keep the ratio 3:1. Then we have the KDA ratio we just talked about. This will be again int and 3. Then for the MOE part, we that is a mixture of expert, we have number of experts, that is int equals to 16, and active, number of active experts, that will be 4, and number of shared experts will be int equals to 2, and the dimension of latent mixture of expert int equals to 256. So latent width for routed experts, that is 0.5 times the dimension of model. Then we have dimension of expert, this will be int equals to 512. And then for the attention residual, we have number of attention blocks, this will be int again and 4, and the gmin, that is lower bound on decay, so as discussed during the explanation, that is negative that is negative 5.0. chunk size is equal to 64, And then for the SiTU-GLU parameters, we have beta 1 SiTU float equals to 4.0. Then we have beta 2 SiTU float equals to 25.0, and then we have vocab size. I think for this we are keeping it as 32,000. Max sequence length is 4096. Dropout float, let's keep it 0.0, no dropouts. And EPS float equals to 1 e to the power minus 6. And we will just simply invoke this class config KimiK3. Okay, so the next part will be creating the components or the building blocks. So first let's create the class of root mean square normalization RMSNorm. This will inherit nn.module class, and this RMSNorm is used like throughout KimiK3, so we are making it a common class. So the first thing is the init function or init method. This will have self comma d, that is the dimension, comma EPS, that is float, not 1.8, sorry, e to the power e to the power minus 6, sorry, not 1.6. Okay, AI has pre-filled it. Let's see. Okay, we are calling the super init self dot gamma. Nope, this is not good. Self dot gamma will be nn dot parameters and torch ones of dimension d, and okay, so it was correct, just not initialized or not properly named. Okay, then the forward method for this, forward self comma x, that is the torch tensor, torch dot tensor, torch dot tensor. This will return torch dot tensor, and this will have root RMS equals to torch dot sqrt, and let's see if I is doing it correct. X to the power 2 dot mean of -1, keeping the dimension true, plus self EPS. This is correct, and we return x divided by RMS star self dot gamma. Okay, next class we have to write is ShortConv class. This is basically 1D depthwise causal short evaluation. It is applied to Q and K query and key vector in KDA for local context awareness. This basically gives the model information about local token neighborhoods that pure linear recurrence would miss. So this will again have nn.module class. It will have as its parent class. Then we have the init function. So yeah, init self comma d comma kernel size. Let's set it to 4 by default. We invoke the super init, then self dot conv equals to nnconv1d. Let's see if it is correct. In channel, this is the in channel, that is d. Out channel is again d, the dimension basically. Kernel size, this is fine. Per padding will be kernel size -1, not divided by 1. This will be -1. This also because causal padding on the left, and the groups equals to d is the depth-wise each channel independently, and we will do bias equals to true. I will explain like what's happening here. Let me just finish this class, and we have to remove this, and we have to remove this as well. This is sufficient enough. Then we have def forward self comma x torch dot tensor. Torch tensor, it returns torch tensor, and like it has argument like batch comma sequence length comma d. X is the size, the shape of the x is like that, and the output shape is also same. So this is have x equals to x dot transpose 1 comma 2, because the conv1d expects the shape as batch, channel and length. So we have to change the order from batch sequence length and the dimension to batch dimension and sequence length. And x equals to self dot conv v of x, and x equals to x of colon comma colon. We are just removing the causal padding on the right. So x comma colon size shape, not size, it should be shape of 2. Oops. And we will then finally return. Again we will do the transpose because it expects the shape as batch, sequence and dimension. So x dot transpose 1 comma 2. So what's happening here is like ShortConv is a depth-wise causal convolution. Each input channel is processed independently, like groups equals to d. Where is it? Yeah, here. And the padding is designed so the position t only sees position less than equal to t. This gives each query and key vector awareness of its local token neighborhoods. The 3-4 tokens immediately before the actual token it's working on. Pure linear recurrence encodes positions implicitly through state updates, but the convolution adds explicitly like local context that can be very useful for detecting local syntactic patterns. So the next class that we can now write is the SiTU-GLU. I'm sure I'm mispronouncing this name, but okay. Dot module so this is like the activation function with like sigmoid tan h unit GLU, It as we discussed, it replaces the SiTU-GLU with the bounded variant that prevents activation explosion in the deep routed expert chains. So first let's again write the init method. So it will have self comma d in, that is the input one, comma d out, comma beta 1, comma okay, so beta 1 can be we can keep it as default 4, beta 2 can be 25. So 4 into 25 will be that 100 boundary that we discussed. And then we initialize invoke the super init method. We assign self.beta1, self.beta2. This is okay. So this is the w gate, and this will be NN linear correct, d in, d out, and bias will be false. Similarly, this w up, this will be NN dot linear, d in, d out, and bias equals to false. And now we write the forward method. I will again like explain once I'm done. Let me just write it. In the forward, it accepts again self and the torch tensor. Then the gate input will be equals to self dot w gate, and up input will be equals to self dot w up with x as its parameter. So the gate branch that is beta 1 multiplied by tan h of x by beta 1 and then multiplied by sigma 8 of h. So the gate will be equal to self dot beta 1 is multiplied by torch dot 10h of gate input divided by self dot beta 1 and multiplied by torch dot sigmoid and gate input. And the up branch is as it was in the formula, beta 2 multiplied by tan h of x divided by beta 2. So this is the soft cap that is on top of the pedal, so it prevents the explosion in the activation. So this will be self dot beta 2 star torch dot 10h up input divided by self dot beta 2, and we do not need softmax here. Okay, and finally we return the element wise product bounded by beta 1 star beta 2. So we return gate star up. So self dot beta 1 star torch tan h. So as I told, this is the soft cap for small input 10h by x divided by beta 2 will be roughly around x by beta. So beta multiplied by 10h x divided by beta is equals to x, that is linear behavior. For large input 10h will be plus minus 1, so beta star 10h will be equals to plus minus beta, saturated behavior. The sigmoid factor gives the smooth non-linear of swish near 0. The product of two branches bounded by beta 1 and beta 2, no matter what. The next class we need is the quantile balancing. So like quantile balancing, as we told, not one expert gets saturated with request and others are sitting idle, so it evenly distributes the token load on each expert. As we are doing it auxiliary loss-free expert load balancing. So QB Analytics derives the optimal bias in one forward pass by finding the quantile of margin scores that would give each expert its target load. The bias is frozen at inference time. So we will then first write init. Again, this will have self comma n experts comma n active comma n bins. So n bins by default will be equals to 200. Let's keep it 200. And yeah, so simple. We will just assign self dot n experts as experts, self dot n active as n active, and n bins as n bins. And we like current expert biases update each training step. So self dot biases will be equal to torch dot zeros of n experts. Okay, so the next method in this class will be compute cutoff, and this will have self comma scores, and scores will be again torch dot tensor of shape batch comma n experts, and it will return torch dot tensor. Let's remove this first. Okay, so this will just give the top like k plus 1 scores. The k plus 1th one is the margin cutoff. For each token we compute this k plus 1th highest score, the cutoff that defines which experts are in versus out of the top k. So this is a pretty simple method. We are just going to have top k scores and comma underscore from scores dot top k and self dot active plus 1, and dimension is -1, correct, and we return the top k scores of these can be done by this way. Yeah, I think I misspelled top k. Yeah, here as well it should be top k. Okay, so we return the the k plus 1th one in the margin cutoff. Then we update biases. We have again self, then scores. This is again the shape of batch comma n experts, and it returns the, let me just copy paste it, torch tensor. So this compute new expert bias until quantile estimation. So for each expert j, the bias should be set so exactly q tokens chooses expert j. So for this again we will first have the batch size of scores shape 0, shape of index 0, and we have target load as batch size star, yeah, this is correct, q tokens per expert, and target quantile equals to 1 minus self dot n active divided by n experts with torch no grad. We have biased scores equals to scores plus self dot biases and this will be biases dot to score dot device. So it is on the same device, and we have cutoffs equals to self dot compute and pass the bias scores. Then for the margins equals to scores minus cutoffs and unsqueeze 1. So now for the new bias for each expert, we first initialize the new biases equals to torch dot zeros self dot n experts. So now we initialize it with 0. We loop it for j in range self dot experts. Okay, expert margin, let's see, this is correct, and quantile, no, this is not good, quantile value equals to torch dot quantile, this will have expert margin and 1 minus the target quantile. So expert margin dot float and 1 minus the target quantile, basically the upper quantile, and the new biases will be equals to the negative of quantile value. We then remove the after like finishing this loop, we then remove common offsets. Doesn't affect the top k selection. So new bias is equals to a new bias minus new biases of mean, and self the final result will be self dot bias is equal to new bias, and we return the self bias. Am I missing something? Oh, it should be inside. Yeah, okay. And then we define the route. Self comma score, then it will be the torch dot tensor. This will return the tuple for torch tensor comma torch tensor. So basically we apply bias top k routing. Bias only affects dispatch selection, not the routing weights used for expert aggregation. So this will have the bias score equals to score plus self dot bias dot to the score of the device. Score dot device. Then it will have the top k selection using biased score. So biased dot top k. Yeah, bias scores dot top k self dot active dim -1, and this should be underscore and top k indices. We do not need to return that. We have to first route weights from unbiased scores. So selected scores is equals to scores dot gather 1 minus top k indices, and did I miss something? Oh, this is not score, this is scores. Yeah, that's why it was complaining. Yeah, fine. And then the weights equals to selected scores divided by selected scores dot sum. This is fine. Now we return the top k indices and weights. So the critical design point here is the separation between dispatch and weight. Biased equal to score plus self dot biases. The bias is added to score only for top k selection, which which expert to send token to. But weights equals to selected scores divided by selected scores dot sum. This is the actual mixture weight. Use the raw unbiased scores. This mean QB corrects load imbalance without corrupting the gradient that train the router. The router always gets accurate gradient feedback. Now we write the stable latent MOE. Before that, we have one more class, that is expert feed forward neural network. So again, similar thing. Let me scroll up a little bit. Yeah. And def we define init. Let's see. Yeah, self dot d model. Let's say self comma d latent comma d inner comma beta 1 comma beta 2 super init self dot SiTU-GLU, again d latent d inner beta 1 and beta 2. We calculate the gate and the up. Sorry, this time it's the act and the down. So down will be n linear, d inner, d latent, and biases false. And the forward, let's write the forward pass. So this will be yeah, it can also be written in a single line return. So yeah, this is good. Yeah, so this is the expert.ff feed forward neural network class. So like if you are like getting too long for you, if this video is getting too long for you, the entire code will be in the description as well. You can drop out if you got the concept. Otherwise, if you want to follow along, just follow along. So the next class will be stable latent MOE and dot module so the feed forward layer, this is the feed forward layer of Kimi K3 basically. So this will have def init self comma d model comma d. Oh, we do not have to write that, we have the config actually. Yeah, and this will be Kimi K3 config. Yeah, and okay, yeah, we can initialize everything from the config itself. So we will first call the super dot init, then let me rename these. So d will be equals to config dot d model, and let's say L for the LatentMoE equals to config dot d latent, and let me remove these. For the shared experts, self dot shared experts equals to nn dot module list, and let me just remove this. This will be nn dot sequential, and this will have SiTU-GLU activation. This will again d comma config d expert, and yeah, now it's correct. And then we have the nn dot linear layer, that is config d expert comma d, no, not L, this should be d. And after the sequential we have for, this will have number of shared, the range in number of shared. What is missing here now? So nn dot module list, this is bracket is correct, nn dot sequential, it opens up SiTU-GLU. This is not right. Okay, yeah. Now for the routed expert we have self dot w down equals to nn dot linear d comma l comma bias false, this is correct. And this is the down projection, and like for the router we have self dot router equals to nn dot linear d comma config dot expert comma bias false, and self dot experts equals to like the expert pool operating in latent space. So self dot expert equals to nn dot module list and expert ffn comma L comma config dot d experts, config dot beta 1 SiTU and config dot beta 2 SiTU, and this will be looped for each expert. So this AI wrote it correctly. L is similar to this L, so why it is complaining? Oh, I am not inside the definition. Okay, that was an indentation error. Now for the upward projection we have self dot w up, and this will be equals to nn dot linear L comma d comma bias false, self comma norm before up, we normalize before the upward projection, so this will be RMS and just not just L. And now the load balancers self dot QB, that is quantile balancing, self dot n active equals to config active, and self dot n experts equals to config dot n experts. So this is the initializing class. We now have to write the forward method. So the forward method will be self comma x, that is the tensor, and one more, that is update biases are not. This will be a bool, yeah, and this will return So this is update bias is because true during training, false during inference, and it returns the torch dot tensor, and the shape of x is b comma s comma and d and equals to x dot shape. So that is batch and sequence length and model dimension dimension of the model. And we have the shared experts path. So shared experts path equals to, so shared out equal to sum of expert of x for expert in self dot shared experts. Then routed expert path. So step 1 is project to latent space. Z equals to self dot w down x. This should be x, and z flat equals to z dot view. So basically flattening the routing. And the step 2 is compute route scores. So x flat equals to x view b comma d, and routed score equals to torch dot sigmoid self dot router x flat. And so this is like computing router scores, and this is not router scores. And then we have step 3 is update the QB bias. This is for training only and route. So if update biases and self dot training, then we update the biases self dot qb dot update bias with router scores dot detach, and we then initialize or assign indices with the updated router score. And then the step 4 is run selected expert on latent vectors. Like for each token we run its k selected experts and aggregate. So this will be u equals to torch dot zeros b star s star multiplied by s comma self dot not self dot z flat dot shape -1 and device is egg device. Type we can omit. And for token id x in range b multiplied by s, so this will be token underscore z equals to z flat token index. This is the L comma 0 shape. Then we have token weights. So token indices, then token weights. So these are both k comma 0 shape. Now we aggregate experts output weighted by routing weight. So for expert I comma expert idx index comma w in enumerate of token indices dot to list and token weights dot to list and so inside we have a u token index equals to w plus equals to w star the expert output unsqueeze. So the expert output is basically self dot expert for in the expert index, and we invoke that with token z dot unsqueeze. And the step 5 is applying the RMSNorm before up projection, the stable in the stable latent MOE. So u equals to self dot norm before up, and step 6 is up project back to full width. So routed out equals to self dot up, and we change the projection to view with view B, S, and D, batch, sequence, length, and dimension. And finally we return shared output plus routed output. So the nested loop over tokens and expert is pedagogically clear but not production efficient. In practice, you would use grouped GEMMs or scattered gather operation, but the logic is correct. For each token, we project to latent space, route through k selected experts, aggregate with routing weights, and then we normalize and then project back. The norm before up is the critical stability addition. Before this, U is weighted sum of expert outputs. Its scales depends on which expert were selected and their output magnitudes. The RMSNorm standardizes this before passing to W up, preventing the scale variation from the routed path from disrupting the combined output. Now we write the Kimi delta attention class. So this is the efficient linear recurrent attention. So Kimi delta attention, this will be again nn dot module, and this will be def self comma config KimiK3. So basically extend the delta rule with channel-wise decay, lower bound log decay via scaled sigmoid, short convolution on Q and K for local context, then L to normalize Q and K, and full rank data dependent output gate. Basically the recurrence formula that we saw in the first slide. So the init function will be like super, and the init function of super, we have the d as d equals to config dot d model, self dot number of heads, self dot dimension of head, and chunk size, all getting from the config. Just one more config is missing, self dot g min. This will be all we will get from config dot g min. Then we have the QKV projection, WQ, WK, and WV. This are the three linear layers. This has config, or we can just say simply D as the dimension of the model. Yeah, and then number of heads multiplied by dimension of heads, and bias is false. We have the output projection. Before the output projection, we need short convolution for Q and K. So self, I am sorry, self dot conv underscore Q equals to ShortConv config. We can take it directly from config, or we can take it from self dot head as well. This will be self again. Yeah, and Kernel, we do not need kernel size right now, so by default it will be taken as 4. And we have similarly we have the conv k here, convolution ShortConv for k value. So this will be again similar, number of heads multiplied by number of dimension of the head. Now we write a strength beta like the scalar sigmoid per head. So this will be, what is wrong here? No, we do not need it. No, we do not need for it the v. So self dot w beta equals to nn dot linear d comma config dot number of heads comma bias equals to true this time. Yeah, self dot number of heads and config is same, so let's do it like that only, or let's replace it self. Now we have the now we write the channel wise decay, d rank, that is the equals to d rank, not range. D rank equals to max of 16 comma d divided by 16, so a low rank bottleneck. And this will, now the decay will be self dot w decay down. This will be a linear layer again, linear, and d comma d rank comma bias equals to false, and self dot decay up equals to nn dot linear d rank comma self dot number of heads multiplied by dimension of the head, that is d. Sorry, dimension of the head is not d, that is self dot d head. Yeah, and for head specific bias for decay we have self dot b decay equals to nn dot parameters dot 0 and self dot heads and comma 1. This is fine. Now for the output gate, we have self dot w gate equals to nn dot linear d, that is number of heads, so self dot number of heads multiplied by dimension of the head, and comma d, and bias will be false. Oh, sorry, my bad. This will be d comma this is the output gate with full rank, and the output projection will be self dot w output equals to nn linear. Yeah, now it's fine. And the headwise RMSNorm on recurrent output will be self dot head norm equals to RMSNorm self dot d head, not number of heads, just self dot d head. Okay, let me just remove this for now. So this is the init function for us. Now let's write the compute decay function or method self comma x dot torch tensor. This will have shape as correct, b s as x dot shape, decay will be, before that we have to have the low rank projection to decay logits z. So z equals to self dot w decay up, not down, and this will be on self dot w decay down. Yeah. And z equals to z dot view b comma s comma self head. We do not need transpose here. And then we add head specific bias, so z equals to z plus self dot bdk unsqueeze 0, and then we have the lower bound log decay via a scaled sigmoid, so a equals to self dot log a dot exp dot unsqueeze 0 and log decay equals to self dot g min star torch sigmoid a multiplied by z. Oh, sorry. Yeah, this is fine. And then we convert to retention factor, that is alpha equals to torch dot exponent of log decay, and we return the alpha. Okay, so the next one will be a recurrent forward method. Did I miss something? Oh, indentation. Okay, now it's fine. So this will be def recurrent forward, and this will be self comma q torch tensor k qkv and the alpha and beta as well. So it missed the beta part, comma beta torch tensor, and it will return the torch tensor. So this is the sequential recurrent forward pass. Clear but slow for like reference. Production uses the chunkwise form, but since we are on a single machine, so we have to go with this. So it has a batch, the sequence length, head, and the dimension of k, so dk. So q dot shape device equals to q dot device, or okay, it's not okay, fine, we can add it here, it's only, and dv equals to v shape -1, and outputs will be equals to empty array. Let me remove all of this for now. And so we initialize state to 0, so s equals to torch dot zeros b h dk and device and dv as well, actually, then device, yeah. And okay, we can add d type as q dot d type. So next we now have the for loop. So for t in range q dot shape 1, we have q t as q with colon comma t and kt and vt. So this will have the shape of b, h, and d head. We have we missed it missed the alpha t. So alpha t will be equals to alpha t and beta t, yeah. And the state will be let me remove this. Now we have the state, step 1 is applying channel wise decay to state. So state equals to state star L alpha t dot unsqueeze -1. And the step 2 is delta rule erase, like remove projection of state onto KT direction. So K, this is the step 2, K read equals to torch dot E in some BHK is comma BHKV pointing to BHV. So this will be equals to there is one, yeah, KT comma state. This is fine, and the erase will be equal to torch dot E in some and beta T. It missed the beta T comma KT and K not state. This will be K read and state equals to state minus erase. So whatever we calculated, what needs to be erased should be erased from the state. Step 3 is writing the new association. So write equals to torch in sim. This is good, but it has beta T comma K of T comma V of T. State equals to updating the state with the new information. Then we read the updated state using the query. So O of T equals to torch in sim, E in sim, Qt and state. And we append it to the outputs, and we return the torch stack outputs. The next method will be chunkwise parallel forward. Like within each chunk we have this parallel matrix operation. Across chunks we have sequential state propagation. So let's define that, and after that we have the forward method. So chunk wise forward will be equal to self comma so sorry, as I was saying, for the chunkwise parallel processing or chunkwise forward, we have self comma q comma k comma v comma alpha, and we have the beta as well, torch dot tensor, and bsh again bsh and d of k will be q shape. C is equals to self dot chunk size, c equals to self dot chunk size, and n chunks equals to s plus c minus divided by c, and outputs equals to empty array. Perfect. I feel this video is getting too long, so let me just finish the code, and if I type it for On the video, it will be even longer because we have a lot of classes to write again. Like we have after completing this KDA, we have gated MLA, then we have log attention residual, then we have pre-head Muon optimizer, and then we have to write the complete K3 block with all of these in one place. Let me write the complete code, and then I will go through it quickly before closing the video. So I will be back once I have written the code. Okay, so I have completed the code. I will put the link in the description. So we were writing the chunkwise forward. So before that, let's quickly do a small recap here. The compute decay method, because it's the most novel part. So the decay logics go through a low rank bottleneck. This is a parameter efficient instead of a full d cross n number of heads multiplied by dimension of head projection. We use a rank d-rank factorization. The head specific bias B decay then shifts the logics per head, allowing each head to have a different baseline decay rate. And the log decay is the lower bound parameterization, and A equals to exponential of log A is a positive head scale initialized to 1 since log A is equals to 0. Multiplying by A before sigmoid controls the slope of the mapping, and the gmin multiplied by the sigmoid maps to gmin comma 0. Then taking the exponent of the log decay gives retention factor in e to the power g min minus 1, that is equals to 0.0067 comma 1, as we discussed during the theory part, and then we finally return the alpha. So this is the recurrent forward function. We just call all the we pass through all the tensor tokens, and we get the output, and we stack on it. So basically it has the read erase, read and write and read operations, and what else? The step one is the apply channel wise decay, then we use the delta rule to erase, then we write, and then we read. So this is the 4-step recurrent forward method, and we left at a chunkwise forward. So this is the the parallel forward pass. The key mathematical objects are the gamma, this one, it is the cumulative product of alpha with the chunk, tells us how much each position decays relative to the chunk start. And we have the k scaled, that is the rescaled keys that makes the intra chunk attention formula works out correctly. And we then have VE equals to V underscore C minus K into S. This is the pseudo values that account for delta rule erase before the write part. And then we have the forward method for this Kimi delta to apply the Kimi delta attention. Then the next component is the gated MLA, and so in this we simply have the init and forward method. So in the forward method, like we basically apply the low rank KV compression, and we do not have the positional encoding on Q and K, and full rank output gate, same pattern as the KDA. So this is the gated multi-head latent attention. In this, the single line is the this C equals to self dot WKV compress is the single line KV cache saving. Instead of storing full n heads dot across D heads key and value vectors per token, which is 2 times n h into D heads equals to around 1024 floats in our small config. We store only the D latent KV, that is of 128 floats per token. So at 1 million tokens, this is an 8 times reduction in KV cache size. And no positional encoding means the same KV cache entries can be reused as in when the model's position changes. So there is no angle that needs updating. So this is another practical efficiency gain for long context serving. Then we have the class for block attention residual. This is the scaling information flow across the depth. So each layer can selectively retrieve a representation from the token embedding, always included, all completed block summaries, the current block partial summary. Like in this, the self dot pseudo query this equals to an n parameter, this line, the W in the diagram, it's a single d-dimensional vector, not input dependent. Every token in the sequence shares this same pseudo query. This might seem limiting, but it works because the attention is over the depth dimension. Which layer to attend to, not the sequence dimension. The pseudo query learns what kind of information is useful at this stage of processing and applies that globally across all tokens. And self dot key norm normalizing key before attention is critical. Without this, a layer that produces activations 10 times larger than average would dominate all attention weights regardless of actual content relevancy. So then we had the pre-head Muon class. Before that, we wrote a function for Newton-Schulz method for approximating matrix orthogonalization. So the in the pre-head Muon class, this G G head dot equals to G dot view, this line, this reshapes partitions the QKV gradient matrix along the head dimension, and each head gets its own like D head comma D in slice. And Newton-Schulz 5 orthogonalizes each head's gradient independently. This result is resembled like G ortho dot view, which passes the number of heads multiplied by D head comma D in. The update this line, update equals to update star G norm divided by update dot norm plus 1 e to the power minus 8 rescales the orthogonalized update to match the original gradient's norm. Newton-Schulz produces a unit Frobenius norm matrix. We scale it back to the gradient magnitude so the effective learning rate doesn't change. And finally, like the Kimi K3 block to like one transformer block in Kimi K3, It contains either KDA or gated MLA for attention, stable latent MOE for feed forward, and block attention residual, and then finally prenorm with RMSNorm. So this is the basically the a single block of all the components we defined above or wrote above. Yeah, after that we had the Kimi K3 complete architecture. This is like from token embedding to the original that number of blocks, 3 KD plus KDA plus 1 gated MLA, and then multiplied by stable latent MOE, then the block attention residual across all layers, final gated MLA layer, and LM head. So this class is the starting point for the code if you want to read the code from scratch. So yeah, go through the code. I will link it down. I have also like written a small test for it, or like just to run it, not a test, just to run it and check if the code is working. And yeah, so like if this ends this video, like to give you a quick recap, like what we did today. So we coded discussed and coded Kimi K3, that is 2.8 trillion parameter model. We obviously didn't train that, but because we don't have the resource, but we implemented every one of its 7 core architectural innovation from scratch in PyTorch. So to quickly go through what each component were, so these are KDA, the Kimi delta attention, a linear recurrent attention with channel-wise decay and delta rule, gated MLA, the latent KV compression that makes 1 million token caching practical without positional encoding. The other one is block attention residual, giving every layer a direct line to every previous block representation. SiTU-GLU, bounded activation that preserves a SiTU-GLU smooth behavior near zero while capping output at beta 1 star beta 2. Then the quantile balancing, that is the load balancer, analytical computing, the optimal expert routing bias in one forward pass instead of slowly iterating. And the stable latent MOE, routed expert in latent space, shared experts at full width, and RMSNorm before the up projection. So if like for 896 experts, 16 active, and sparsity of 56. Per head Muon, so Newton-Schulz orthogonalization per attention head equalizes learning dynamic across heads regardless of gradient magnitude difference. So today's video, as I said, we had a different pedagogy, and that was good actually, because this architecture was huge. So we discussed the architecture first and code all at once, or like we started coding, but the video went so long, so I just finished it and recording went through it. Let me know in the comments whether you prefer this approach or the explain then code approach from the previous videos. This will help me get the direction for the future videos. Full code is in the description, and if you like the video, subscribe, tell me what other research paper you want to see, or what other video idea I should work on, or any other AI topic you want me to cover. And yeah, thanks for watching. See you next time.